This video is an example problem where we're going to use Newton's second law to solve the problem, or as the backbone of the solution of the problem. But within the problem, we're going to have to model the situation with a whole bunch of different weights and a slew or a bunch of normal forces. So this problem, it's just an example. So it's a problem of having an elevator that is accelerating upwards because a rope is pulling up on the elevator. And inside of the elevator is a table. And on top of the table is a box. So I got a little box. I have a table inside of the elevator and a rope pulling up on the elevator, and the acceleration of all of this stuff is, I'm going to give it a value of 3 meters per second squared, and we'll say it's upwards. So the acceleration vector. If you think about it, in this case, something that I'm going to ask you to assume, and it's probably what you would assume anyways, is that because I have a situation of the elevator going upward or accelerating upwards, it's not necessarily actually moving upwards, but it is accelerating upwards. It could be going down but slowing down, for example. So going down with an upwards acceleration is going down and slowing down. That's an example. But the point is that the acceleration of the elevator is going to, so the elevator is the box on the outside. The acceleration of the little box on the inside, little b for little box, and the acceleration of the table are all going to be equal to the acceleration of that I described as the acceleration of everything here. So they all have the same acceleration. But even if they have the same acceleration, you know that they're not necessarily going to have the same forces involved. And that's what we're going to go and explore, is what are all of the forces on all of the various objects. The objects are the table, the elevator, and the box. And we'll say that the mass of the table, just to have some stuff or some values, is 20 kilograms. So that's about the third of a mass of a person. It's a normal table in your room, maybe. The box is going to be even less mass. So a cardboard box full of eggs, I don't know, doesn't matter. And then the mass of the elevator box itself, this thing right here, it's made out of steel and wood and plastic and other things, maybe some glass. This is probably kind of light for an elevator mass, but let's say it's a carbon fiber elevator. Again, who cares? But here's some values. Another thing that I'm going to put in the background is the fact that this is happening on the Earth. So, and it's happening quite close to the surface of the Earth, where the acceleration due to gravity is about this sort of standard value. This is a vector. I have to remember to give it a direction. None of the masses are vectors. They're all scalars, right? So a bunch of vectors over here, this vector here. Okay, and I'll remind you real quick that the model for the weight of any object is to take the mass of that object and multiply by the acceleration due to gravity where the mass is sitting. So all these masses are sitting in this gravitational field, or this gravitational acceleration value. So if I want to know the weight of, say, the table, I just take the mass of the table, 20 kilograms, and put it right there, multiply it against the vector acceleration, and I'll have the weight of the table. So I'll describe the weight of the table with a little capital T below it, the weight of the box, the weight of the elevator, like this. One thing to wonder about is I did list this other object, the rope, but I'm not going to study the weight of the rope. I'm going to, yeah, I just, it's not an important detail, at least for teaching you how to use Newton's second law and thinking about some of these forces. You could certainly go further and try to wonder what would happen is if we started to consider the rope as another one of the objects. So we just put a fourth object here and put the rope there, give it a mass, etc. But we're not going to do that. Okay, so let's say that the problem is what are all the contact forces? That is, forces because things are touching each other. So I'm calling contact forces, another word for that is the normal forces. So contact forces, these are going to be, I'm going to use the symbol capital N, and it is a force, so there is a vector. This is going to be pretty interesting though. For example, a contact force that I could ask for, and in fact it's going to be the first one that we try to discover, is it's the normal force that acts on the box. And so the box, if you look at it, it's only in contact with one other object in the problem. That's interesting. It's in contact by or with the table. That's the thing we're going to find first. After that, we're going to find what is the normal force, say, on the table by the elevator instead. And then later, I'll ask, well, what's the normal force or the contact force on the elevator by the rope? So these will be some of the forces that we're looking for. Yeah. So whenever you see acceleration mixed in with forces, and there are calculational values around that you can think with, you really ought to be thinking in terms of Newton's second law. And Newton's second law is a law that's very clearly written that the net force on any particular object is equal to the mass of that object times the acceleration of that object. So if I want to find out what is the contact force acting on the box, then I would want to know what is the net force on the box. It's the mass of the box times the acceleration of the box. And the net force on the box is the sum of all of the forces that act on the box. So we're concentrating on the box. We don't care about any other object, actually, when we are studying the box. And the Newton's second law backbone of the problem for the box, we don't really care about the elevator or the table or the bird flying around the outside of the building. None of that other stuff matters. Okay, so here's our problem. So let's say that this was our first goal. The problem is, what are all the contact forces? Let's pick one. This one, it just turns out it's kind of the easiest one. So let's pick this one. All right. So the net force on the box by the table. So this is one of the forces that comprises the net force on the box. So the net force on the box is just the sum over all of the interactions that act on the box because of other objects, and these are all forces. So let's go look in the diagram. This box, here it is. The only thing touching it is the table. So that means at least the table, right? The force on the box by the table, this normal force, that's one of them. So I'm going to list it in my summation. I'll just put it first. It doesn't matter if it's first or last or in the middle. It doesn't matter. By the table. So I've got that listed, but that's not the only force acting on the box. the box also has a weight. This is a force acting upon the box, and it's due to gravity with a gravitational interaction with the Earth. And so actually there is another force on the box. It looks like this. It's the weight force. It's a force on the box by the Earth. And it is, this thing right here is the same thing as this that you calculate this way, where you put the mass of the box times the acceleration due to gravity on the Earth. So I've got this term here is equal ultimately to the sum of these two terms. And if you look real carefully at what I've got, I know this and I know this, but I do not know that, but it is the answer to one of my questions. So I'm going to isolate this and solve for it. Before I do that, here is a skill that you really ought to start building, and so let's try to build it in right now. This is a big time skill.